Okay, so what are we really talking about here? You have your general purpose, good old fashioned CPU, which a lot of us are used to using. And then you have these specialized devices called GPU devices. And so really what is the difference? Well, with a CPU, you really have to have a lot of versatility. A CPU is designed to run multiple types of tasks. It can be, a web server that you spun up on a computer. It could be just a general calculation, utilities like TOP or PS, or even the Slurm scheduler runs as a service. And so those have to be able to process a very large range of instructions and deal with task-related parallelism so that it can provide a very broad range of services. Now for GPUs, those are highly specialized devices. So you're not talking about nearly as many, instructions, a big variation of instructions. You're talking about performing a smaller amount of instructions or the same operation on multiple pieces of data. So the CPU has, a relatively small number of cores, less than 100. The number goes up, but for the most part, compared to GPU, a relatively small number of cores, and those cores have to have a lot more control over what is coming in and out of them. Whereas in a GPU, you have a lot of really dense, lighter weight cores, and the control unit that's associated with those doesn't have to be nearly as intelligent. Another thing to keep in mind is that CPUs are really purposed for task parallelism. So that's what they call the multiple instruction, multiple data programming model, whereas GPUs are more of a data parallel model. And really, if you think about it, they were purposed for graphics processing. And so you're talking about pixels on a screen, which can be kind of viewed logically as a grid, and then just changing the shades and colors and things like that on those pixels. You're performing pretty much the same operation across all of the data on that grid. CPUs are much more concerned about the amount of memory that have available, whereas GPUs are really more concerned about the throughput, the speed at which it can process. And as I mentioned, the control units on these devices, the CPU, each core is pretty much dedicated, has a dedicated control unit with a larger instruction set so that it can understand a wider variety of operations. Whereas on the GPU, you have a little bit smaller instruction set and a lighter weight control unit, or the control unit's actually assigned to groups of cores rather than a single core. And then for your thread management, you have to do a little bit more work on the CPU to get your thread parallelism, whereas on a GPU, a lot of that is automated for you. So those are just some examples of the differences. And maybe that clears up a little bit about how a GPU might apply to your workload. And so a little bit more background. As I mentioned, originally purposed for graphics, and so the intent was to offload some of that graphical overhead from the CPU and move it over to the GPU to speed up things like video games, media, graphics, video editing, and things like that. What people figured out as time went on was that really, okay, these things are purposed for graphics, but really you can generalize that. What if you have a data parallel problem? That is, you're looking in your code and you're seeing, I'm doing a lot of these iterations and I'm performing the same operation on different pieces of data in a loop. And if that's the case, I might be able just to break my data up into chunks and apply the same operation in a more parallel fashion. And then the last two, vector processors and single instruction multiple data, are just some constructs that might help clarify a few things. A vector processor is a hardware architecture that's designed for this type of thing, this data parallelism, as opposed to the general purpose processors, which are much more of a scalar type processor that perform operations on single values one at a time. And so if you look on the left there, you can see the general architecture you might find on a vector processor, which really is taking the same data from the same pool and performing the same operation on that data in different sizes or chunks. Okay, so I'm going to go through this. I just want to mention that GPUs are good for more than just AI workloads, but we hear a lot about artificial intelligence, and there's a lot of buzzwords, and this was really helpful for me to kind of clarify, how to visualize the AI buzzwords that come along a lot of these days. So in the general sense, you have artificial intelligence, which is really just emulating what you see in nature in terms of the way that biological organisms solve problems. And so it's a very general thing. You could, one thing I am somewhat familiar with is evolutionary algorithms, which simulate, it's a population-based thing, which simulates sort of the evolutionary process or the reproduction process that you see in nature in order to solve problems, but also, emulating things like brain and neurological functions, which ties into machine learning, which is a subset or a subdomain of artificial intelligence. And machine learning itself is the ability to teach a machine or to program a machine to learn like biological organisms do. And that happens ideally, independently. With machine learning, you have to provide at least some guidance to your algorithm or your software to help the machine learn. But the idea is that you feed the program a lot of data, and then it will perform some sort of analysis on that data in order to recognize patterns or draw conclusions and then predict outcomes. And so you have things like decision trees or linear regression you can use in machine learning. And that's the broader category before you get into neural networks, which really simulates the way the brain solves problems. And so in the brain, you have neurons, sort of a network of neurons that, based on an input threshold, some sort of input it receives from other neurons in the network, will either fire or they won't fire. And so you have sort of a binary output there, either yes or no, or a 0 or 1, based on the amount of signal it gets from the previous layer of neurons. And deep learning, which is really the same thing as a neural network, it just happens to be a very large neural network, a lot of different layers. And what that does is really add a lot more automation and independence compared to just your older style machine learning algorithms. And so hopefully that helps clear up, some of the things you might hear when you talk about GPU. Usually people equate GPU to AI algorithms these days, but it's more than just that. And here's some examples of libraries and tools that are available for a variety of different scientific workloads. You have the CUDA toolkit and Thrust, which are more general purpose GPU libraries just to provide math functions, linear algebra, or some common parallel algorithms like sorting or decomposition. And then you have things like data science. Of course, you can see physics, genomics, medical imaging, all sorts of things that you can do. Basically, if your problem or your calculation is at least in part performing the same operation on multiple pieces of data, then you can probably find a use for GPU. All right, so just to quickly cover the hardware architecture, because the nice thing about GPU is that the hardware architecture maps very closely to the programming model or the programming constructs. So if you view the hardware of a GPU or the architecture, it's really just a two-dimensional plane of components. And those can be sort of addressed or indexed with a X and Y coordinates. And so you have this grid, this big grid, which is just the GPU, but within that, you have these stream multiprocessors. And then those can further be broken down into X and Y coordinates. And within the stream multiprocessors, I should mention, those have the multiple actual CUDA cores within those. And so to further kind of illustrate that, you see on the left side there, you have your GPU device, which can map to this grid model. So you have multiple streaming multiprocessors within the GPU device. That second row there shows you the first streaming multiprocessor indexed at 0, and then the CUDA cores addressed at 0, 0, 0, 1 within that. So you have a grid, and this is what they call the thread hierarchy, I believe, in the GPU programming. the grid, which is roughly equivalent to the device, the block, which is roughly equivalent to the stream multiprocessor, and then you have your cores, which is the basic unit of execution. So threads are executed on a GPU by the CUDA cores. Generalized workflow for a GPU program is to allocate your memory on the host, initialize your data on the host. And when I'm talking about the host, I'm talking about the machines you're familiar with, the Linux operating system and the CPU and memory that are available in your normal workflow for general purpose CPU workloads. And that host has access to a GPU device. And so you first allocate you first perform your initializations on the host, and then you tell the host, okay, I need to allocate some memory on the device. And that prepares both the host and device to begin the work. Once you've done that, you transfer your data over from host to memory to device memory, you execute your kernels, and if all goes well, you bring your output back to the host, and you've got your results. This illustrates some things in code. So you have libraries which you use in your code to access some of the underlying features of the GPU. It's your interface to the GPU device, so to speak. In C, you might use a pound include with pointing to a CUDA library or whatever construct or framework you're using. And something like Python, it would be a matter of importing the library of interest in order to prepare the Python environment to understand those GPU commands. And this is important to note. In GPU terminology, they have kernels, and kernels are not your kernels, or at least the ones that I'm used to, which are operating system kernels like the Linux kernel. A kernel is really just a routine, a function, or a method that runs on the GPU. And so you can see here on the left, the CUDA hello function, which has been augmented with that _global directive. And when you use the NVIDIA compiler in this case to build that program, the compiler understands that global directive indicates this function is bound for the GPU device. So it's not the OS kernel, but you would actually just kind of mark your functions, the ones you want to run on GPU with that global directive, and those will run on the GPU. Below that, you can see an example of the NVIDIA compiler in order to build a GPU program to perform the linkage and the breaking down the human readable instructions into machine code or GPU instructions. Or an example with Python would just be a matter of instantiating the Python runtime environment or interpreter to decode the Python into machine instructions. And then I mentioned the runtime environment below that. That's just to really emphasize that you, in this case, or in HPC, in the case of HPC, you will need to run through a scheduler. And so here you see the srun command. That's a Slurm command that is requesting a GPU device and telling it to run this particular program, which is called hello. And we'll get into more details on this here shortly. But I want to also point out that when you access HPC clusters, at least the ones that we have here at Auburn, the login nodes, the access nodes like transfer nodes or login nodes, don't actually have GPU devices directly attached to them. So you cannot necessarily test your GPU code directly from the login node without running through the scheduler. But what you can do is you can compile your code there and prepare and do your pre-processing before you use the scheduler to submit a job or to run the code. Or you can actually query the different partitions to see what the status of those GPU partitions are. So we define GPU partitions on Easley. We currently have 2. I'll go into a little more detail on that. We have a GPU 2 partition, a GPU 4 partition, and what that 2 and 4 indicates is the number of GPU devices available on those nodes. But if you want to be able to actually run your code, you'll use sbatch, srun, salloc, any combination of those, to test or run your code, and also to query the device or just monitor the performance of your application. So a little bit more in terms of what the code looks like. Our lab is going to be based on Python, but illustrating the constructs is, to me, a little bit more clear using C, because the Python libraries sort of obfuscate a lot of the CUDA related syntax from you, whereas C is a little bit more explicit. You can see in comparing the standard C++ with the CUDA C++ on the right, that it's really just a couple of minor differences. You have that global directive that we talked about earlier, which tells the compiler that this function is bound for the GPU. And then you have that really strange looking triple nested less than greater than. I'm not sure even what the terminology is for that, but it's appended to the name of the function. And what it does is it tells the GPU how many blocks and threads that you want to run the particular kernel with. So in this case, we're just requesting a single block and a single core. It really should just print one hello world. And that will be processed by the GPU. And then so you have the kernel, which is the function at the top, and then the kernel launcher, they call it, in the main routine down near the bottom. So some minor differences, but very important ones. All right, so what devices do we have on Easley? We have the Tesla T4 GPU devices, 2,500 cores, CUDA cores, and then each device has a 16 gigabyte memory. Yeah. And the two partitions that I mentioned, the GPU2 and the GPU4 partitions, which you can see using that sinfo command or some sort of a similar syntax for the sinfo command there. That S you see at the beginning is a typo, so I apologize. I'll get that corrected. But sinfo-p for partition, this will say, both GPU2, GPU4. And you see down here below that the GRES indicates how many GPUs, in this case 2 and 4, partition name, and the number of nodes within those partitions. So the GPU2 partitions have 9 nodes, whereas the 4, we only have 2 of those. But everybody should have at least some access to those, whether or not you have preemption capabilities or priority access to those is determined by whether or not you actually purchased or invested in GPU nodes. Okay, so how do we begin thinking about using these resources? The main thing you need to know is that in order to prepare the system to query GPU devices, load the necessarily environment settings for compilers, the CUDA toolkit is the main thing you're going to be interested in, and you'll do a module load CUDA 11.0/toolkit, and that will load up all of the necessary libraries, put everything in your paths, and set your environment the way it needs to be. And then once you do that, you can kick off a command, something like this, where you're saying, okay, I want to run on the GPU4 partition this NVIDIA-SMI command. And once you do that, you should get some information on the status of the GPU as seen there in that output. In this case, the GPU is idle, no running processes, so it's fully available for use. But that's just a quick, two-step process for, hey, load up the environment and see what I have available. There's also an NV top command. There's a NV profiler command that will illustrate or demonstrate in the lab exercises. And there are a couple of paths you might be interested in down in the /tools directory, where we house a lot of the different research software. In /tools/GPU, you'll find some directories that'll have sample code, and all your compilers are down there, a lot of your GPU libraries, utilities, and things. But the CUDA simple path there will give you access or show you some of the NVIDIA provided simple program examples for using GPU. We also have the HPC SDK from NVIDIA, which is a little bit more advanced. It does some things like provide examples for how do you do a hybrid approach if you want to use MPI and GPU, for example. So it gets a little bit more complex for the HPC stuff. So I recommend starting if you're new to it, start with the simple code examples and kind of work your way up to the HPC paths. But those might be important for you at some point down the line. All right, so that brings us kind of to the end of our introduction to the constructs and the basic scheduler syntax, some of the tools and utilities that you might run into, and some resources. At this point, we'll look at beginning the lab exercise. All right, well, let's get started real quick. Just to, as mentioned, just a command to kind of, verify you can run the sinfo command to get the Easley GPU partition information. So I'm just going to copy and paste that. And you can see it's very similar output to what we saw in the slides. It's just saying, here's our GPU 2 and GPU 4 partitions, how many nodes and how many GPU devices are available. And then we'll go ahead and move down. I'm just going to, you guys feel free to run through this at your own speed, but just to illustrate how it's supposed to work, I'm going to run through these with you, or quite quickly. But again, we're going to load the CUDA toolkit that will prepare our environment. That's actually the module show. We're going to show the CUDA toolkit, and we can see that it's doing a lot of stuff with our path. It's setting environment variables here. It's prep-ending the path with some bin directories that hold some different binaries and executables. A lot of stuff with the library path. You have some specialized CUDA paths, CUDA home, CUDA root. So if you do a module show on any module, it'll give you a better idea exactly what's involved with using that and how it's manipulating your environment, which is sometimes useful. Really, this illustrates there's a lot going on with this one. It's atypical, so somewhat compared to more of the other, the more basic or the more fundamental research software modules. There's just setting a lot of stuff going on with your environment here. All right, let's go ahead and actually load that. Or actually, no, I'm going to follow the instructions here. We'll go ahead and do an ls on our tools directory and just show you what's down in that CUDA simple path. You can see a lot of code samples here for different things, maybe some things of interest, matrix multiplication, simple printf if you wanted to do like a basic hello world. It says there's a simple MPI use case there. And so just look through there and see if there's anything of interest to you. But more than anything, just be aware that that is available. All right, so let's go down and begin working on our basic C++ example. So we're going to go through C++. I know a lot of people may not have use for that or may not be familiar with it, but I think it will really help to illustrate some of the workflow, the constructs that are involved. So first, we're just going to change to our home directory if you're not already there. We'll go ahead and create a directory to house our code. I think mine already exists. Yours may not. We're going to cd to that directory. We're going to copy the files from down in tools, GPU, tutorials to that directory. Make sure that those files are there. You should have two directories, a hello and a PyTorch. And we're first going to work in this hello directory. All right. So down in there, you'll see yours may look a little different. It probably is going to look like this. Something like that. You should have some CUDA code. And if you look at those files, even though they're a .cu file, they're really just, your sort of a typical C or C++ source code. The standard way that you see a lot of the tutorials online is to end with this .cu instead of just C or CPP. And it's just a way to kind of self-document this is, CUDA code. All right, so now that we've taken a look at that, let's compile it. So have we loaded our module yet? Let's find out. All right, so it's telling me that this nvcc command is not found. And that's because I forgot this first step. Module load, CUDA 11 toolkit. And now we should get a clean build of that program. With that built, if you do an ls, you should see that it's there. Let's do an srun and see if we can actually get results from the GPU device. And you can see, we're going to look at that code again. Can everybody hear me? I had an alert that I was muted. Somebody muted me. Are you guys tired of hearing me talk?
I can hear you.
No, that was me, Bradley. I'm sorry.
No problem. Yeah. Hey, take it over, Keenan. Take it away.
No, I thought that GPU4, I didn't know that was going to work for you. So it was going to be on the ready to.
Oh, yeah.
No, but no, you're fine.
I don't, I put this in here because I was having better luck getting access to the 4 partitions. The GPU2 partition was quite busy up until recently, but
yeah, we had saved that one for you on GPU2, but I think GPU4 is fine right now. So no problem. Sorry about that.
If anybody has trouble, or it says, it's just hanging on trying to allocate the node for you, you may just want to Control C out of it and put in GPU2, because there should be maybe some availability on one or the other. But here we're using the GPU4 partition, which seems to have worked. And remember, we had our triple nested kernel launcher here, which is requesting 6 blocks, each with a single core. And here we have a total of 6 hello worlds. So each of those GPU cores processed this kernel as a thread and sent its results as a printf. All right. So what about this other one? It's a little bit more involved slightly, but just some basic indication of what's available. And you see that in this code, it's just a little bit different than the first one. We have this block idx.x and the thread idx.x, and that's just telling us, okay, what is the block ID and the thread ID that is currently running from the context of the GPU core in which this kernel is running. Give me the IDs, the block ID and the thread ID. And in this case, we changed from 6 blocks, 1 thread, to 3 blocks, 3 threads. So let's see what happens if we build that. Okay, that came back, no errors. So we should be able to run and see what the difference is. And in this case, we should get a little more detail. And here, each of the threads came back and gave us its block and thread ID. So block 2, block 0, block 1. And the interesting thing is, a lot like MPI, if anybody has experience with that, it's sort of an asynchronous execution. You're not really sure which GPU block or thread is going to return first. So you see 2 came back first, then 0 and 1 for whatever reason. But a little bit more detail there, just to sort of point out that, or at least to further confirm that the GPU is running as we have told it, using the 3 blocks and the 3 threads on each. Another interesting thing that you might want to do with your code is to find out where it's spending all its time on the GPU, or if it's spending any time on the GPU. And so you can use, let me just paste this in. And I'm going to shrink this screen slightly so we can get a little better output. Okay. So what I did here was I told srun to run this program, NVProf, or MV Profiler, I think is the NVIDIA Profiler utility. And the MV Profiler is taking a single argument, which is the name of our program, and it's telling us where exactly it's spending its time. In this case, just the basic hello command spent 99% of its time in the launch kernel phase, whatever you might call this, API call, I guess is what it's saying. And it breaks it down into a number of core API calls. So you can see you got the launch kernel, the total mem, get attribute, that kind of thing, and the number of calls for each. If we run that on our other program, we should see slightly different numbers, or at least a little more time spent than some of the other API calls, just because we're referencing the thread and block IDs. And so here, well, let's see. Still, the numbers are the same. The percentages, I guess, are slightly different. But the main takeaway there is you have profiling utilities and monitoring utilities that you can use to, get a better idea of where your code is spending its time, confirm that the GPU is being used where you need it to be, and you can use srun to kind of one-off execute these things on the device. For things like monitoring and checking the state of the GPU, the srun command is quite handy. For a normal workload, you'll probably use sbatch to submit sort of unattended or in batch mode, and then possibly use these profiling utilities within the sbatch to just dump the output at some point in the program and confirm that it's working as expected. But that really brings me to the end of the C++ portion of the exercises. And hopefully that gives you a little better idea of some of the things you can use, some of the basic utilities you can use in the scheduler commands and syntax for using GPU devices on Easley.
All right. So as Bradley mentioned, we'll install PyTorch, which is one of the popular deep learning frameworks. In order to set up and run CUDA operations, PyTorch provides this package called torch.cuda. This package adds support for CUDA tensor types that implement the same functions as CPU tensors, but utilize GPUs for computation. I won't get too deep into what tensors are. We can provide some information for you all. NVIDIA does provide tensor cores, as I believe you mentioned earlier, Bradley. But in this lab exercise, we'll begin with installing PyTorch. In order to do that, we will set up a virtual environment. For those of you who are new to virtual environments, I will provide some information in the chat we have about setting up virtual environments. I will take you through that process within this lab where we'll set one up, activate it, install the packages necessary, and I'll show you how to deactivate that virtual environment as well. All right, so we will get started here. Let's cd to the HPC GPU directory we've created in the first portion of the lab. Let's do an ls. Let's module load Python first to create that virtual environment. Check our modules here. And as you can see, we have Python 392. So next we'll do a Python, and we'll call this virtual environment PyTorch Lab. That just may take a couple of minutes to finish there. Next, what you can do is activate that virtual environment. Let's cd inside of the Python lab here. Let's do a source, bin, and activate. Now this will activate your virtual environment. And now that we have our virtual environment activated, you can install any packages that you need. So let's install the PyTorch package here with pip. That just may take a moment. And just to give a brief point about tensors, PyTorch, in their documentation, they state that tensors are conceptually identical to NumPy array. If you all use NumPy arrays within your workload. And PyTorch provides many functions for operating on these tensors here. All right, so now that that's installed, we can check the packages by doing pip list installed. Just to double check here. All right, and as you can see, we have PyTorch here. It'll show up Torch, Torch Audio, Torch Vision, and any of the dependencies here. So we have the NumPy, Pillow. All right, and just to show you a brief demo on how to deactivate that virtual environment, you just type in deactivate. So the first part of our lab is complete. We now have installed PyTorch. We've activated our virtual environment and deactivated. So next we will briefly go over that Torch CUDA package. So let's run a job here interactively using srun. And I may use the GPU4 partition since that seems to be the lucky one today. And when you wish to access or use any of the GPU partitions, you will have to use this, that GRES parameter. So we'll say GPU, Tesla, and we have 4 available on the GPU4 partition. But in this example, I just want to use 1. And we'll use pty bin bash, just the shell that we would like to use. All right. And that should, let's see if I can open up a new terminal session. Leave my virtual environment. Let's run. All right. And so I'm out on node 700. Let's take a look at our modules here with the module list. We will have to load that CUDA toolkit. So we'll do a module load, CUDA 11 toolkit. Load Python. Let's CD to the HPC GPU, Python lab. And let's activate our virtual environment. So we'll do a source and activate. And as you can see, our virtual environment is activated, and you can tell once you see the name of the virtual environment here on the left. So now let's do a Python 3. And let's import PyTorch. All right, to check if your system supports CUDA, you can use the following command, the is available command, which will either return it'll return a bool value if either true if your system supports CUDA or false. So we'll say torch.CUDA, and let's check if it's available. That's a really great command to use when you're troubleshooting and testing for the first time using PyTorch. Let's see, let's also use this current device command to provide information about the ID of the CUDA device. So torch.CUDA current device. And it brings back this ID value of 0. So let's take it a step further and provide some more information about this device. So we'll say torch CUDA. Let's check the name of this device here. It'll bring back Tesla T4. And just to provide even more information, let's use the torch at CUDA. Let's get the properties of this ID value here. And it will provide some more information here. So it's Tesla T4 is the name. This is the total memory here, which is about 15 gigs here. And let's exit here. And as Bradley mentioned before, let's see the NVIDIA SMI, I believe that's the command. We'll just take a look at some of the information here and compare it. So that Tesla T4 ID of 0 has that memory usage here. So we have around 15 gigs of memory we can use. We're currently not using any. And you can use this command to, if you're running any processes, it'll list some of the processes in this area here. Okay, so the next portion of this lab, let's see if I can clear my screen here. I'll just copy this Python script here. And let me do a more on that. So this is a sample code that PyTorch provides. They have really great documentation on their website on how to get started. They have videos, labs, and code that you can follow along. Here, it will import the torch, import math, do some basic arithmetic functions here. As you can see, it's pulling the torch device CUDA, and it's pulling that Tesla T4 ID 0 device there that's allocated to us. If you wanted to run this just with CPU, this is the option that you would choose for CPU. And let's see if we can run this code here. So I'll just execute it. Now just take a moment. And if you all have any questions throughout this lab, please feel free to paste in the chat. I will provide some more information on PyTorch and their getting started page with their labs and tutorials. All right. So at this moment, we will deactivate the virtual environment. Once more, let's exit off of this interactive session. And let's see if we could submit that same PyTorch script within a batch submission job. All right. Go into HPC GPU. And let's see, I believe there is a lab.sh within this PyTorch directory here. I'll do a more on that lab here. So in this submission script, we have selected the GPU4 partition. We've selected the time. We only want one node, one core. And although we have 4 available, we would only like to select one of the GPU. Specify the name. So in this script here, you will have to load the Python module and load the CUDA toolkit. And if you're using a virtual environment within your batch script, you will have to use that source in order to activate it. That's something I've seen researchers kind of have issues with in the beginning. They'll set up a virtual environment, they'll install the packages, and then they may get some errors. And that's because they didn't activate their virtual environment before running their code. So after you activate that virtual environment, then you can do a Python 3 on that pytorch.py code here. And you can also, we're going to place it inside of a text file. All right. And just to go back to that, since we have this PyTorch within the same directory, we won't have to specify a full path. But if you do have that Python code within a different directory, just make sure you have the pathing right. That's also an issue we've seen in the past. So we'll just do an sbatch lab.sh. And as you can see, I've created a job here with the scheduler. And we can see it's running. And that just may take a couple of minutes. The results aren't there yet. We'll just take a moment for it to finish there. Now, so that's finishing here. I wanted to paste this PyTorch tutorial for beginners into the chat. They give you some more information about tensors and their use of tensors. You'll start out with a lab exercise without using the GPU component, and then you'll move into using PyTorch tensors. Okay. And the results are there inside of our results.out file. And with that, the lab is complete. If you all have any questions, feel free to let us know in the chat, and I will turn it back over to you, Bradley.
I'm familiar with the